Dear students, continuing our class on anaerobic treatment systems, we will discuss in more detail the high-rate systems, specifically focus on the attached biomass growth in these reactors. In the figure, we can revisit the proposed classification of anaerobic treatment systems. In the last lecture, we discussed conventional systems in more detail. In this class, we will focus on high-rate systems, with the main technologies highlighted here. With the advancement of research in anaerobic treatment, high-rate systems have been developed. These systems are primarily characterized by their ability to retain large quantities of highly active biomass, even under conditions of low hydraulic detention times. As a result, a high solids retention time is maintained despite the application of high hydraulic loads to the system. This leads to compact reactors with smaller volumes compared to conventional anaerobic digesters, while still achieving a high level of sludge stabilization. The concept of attached bacterial growth requires the development of bacteria joined to an inert support material, leading to the formation of a biological film, that is the biofilm. A more commonly known example of reactors with attached bacterial growth in a fixed bed are anaerobic filters, as shown in the figure. These reactors are characterized by the presence of stationary packing material, where biological solids can either attach to or be retained within the interstices. The mass of microorganisms attached to the support material or trapped in the voids degrades the substrate in the wastewater flow. Although the biomass is occasionally released, the average solids residence time in the reactor typically exceeds 20 days. Therefore, it can be observed that the average residence time of the microorganisms in the reactors is quite high, as they remain attached to the support medium, which enhances the overall performance of the treatment process. The long solids residence times in the reactors, combined with the short hydraulic retention times, give the anaerobic filter significant potential for treating low-concentration wastewater. A large portion of biomass exists as suspended flux, which are retained in the voids of the support medium, interstitial retention. This had led some researchers to argue that the shape of the support materials is more critical than the type of material used. The design and structure of the packing material play a key role in the system's ability to retain biomass and optimize the treatment process, highlighting the importance of its geometry in achieving efficiency wastewater treatment. Here we can see examples of support media for anaerobic filters. The anaerobic filters are typically operated with a vertical flow, either upward or downward, with upflow being the more commonly used configuration. In the upflow setup, the liquid is introduced at the bottom, passes through the filter layer, support medium, and exits through the top. In contrast, the downflow configuration involves introducing the wastewater at the top of the filter, above the support medium, and collecting the effluent at the bottom of the reactor. Downflow reactor can be designed with either a submerged or non-submerged supporting medium. Effluent recirculation is more commonly employed in this second configuration. This approach can improve the efficiency of the treatment process by enhancing contact between the wastewater and the biomass within the reactor. The main disadvantage of anaerobic filters is the accumulation of biomass at the bottom of upflow reactors, which can lead to blockades or the formation of hydraulic short circuits. In this regard, download filters are more sustainable for treating wastewater with higher concentrations of suspended solids, as they help mitigate the risks of biomass buildup at the reactor's bottom. This configuration ensures better flow distribution and reduces the potential for operational issues related to clogging or short-circuiting. Here we can see some photos of the installation of anaerobic filters. In the first photo, the reactors are still empty. In the second photo, after the placement of the support medium used. And here is the biogas collector. Another fixed bed anaerobic reactors alternative is the rotating bed anaerobic reactors that consists of a rotating filter bed made of materials like plastic, which provides a large surface area for anaerobic microorganisms to grow and degrade organic matter in the wastewater. The continuous rotation of the bed ensures that bacteria are constantly exposed to organic material, improving the efficiency of the degradation process. This rotation also helps maintain a uniform flow distribution, prevents clogging, and creates an optimal environment for anaerobic bacteria to thrive, enabling effective removal of organic matter and suspended solids. In sequence, there is a settler for the removal of suspended material. The relation of solids retention time and hydraulic detention time is very high, and blocking should not occur in the system. since the rotation speed of the disks is such that the shearing forces promote the removal of excess biomass kept between the disks. However, care should be taken in the transfer of results obtained in the laboratory to full-scale plants in the scaling up, as the rotation speed substantially increases with the increase of the disk diameter. In high rotation speed conditions, the shearing forces can prevent biomass attachment. This system is notable for its simplicity, low energy consumption, and ability to handle varying wastewater loads, making them sustainable for small to medium-scale applications. Since the process is anaerobic, there is no need for constant aeration, which reduces energy requirements compared to aerobic systems. In this photo, we can observe a sewage treatment system consisting of an anaerobic biodiscs followed by a settler. Another technological alternative is the expanded bed anaerobic reactors. The development of the expanded and fluidized bed anaerobic reactors practically eliminated the problems of the limitation of substrate diffusions, usually inherent to the stationary bed process. The expanded bed reactors consists of a cylindrical structure packed with inert support particles to about 10% of its volume. Several typical materials have been used as a support medians, including sand, gravel, coal, PVC, and resins. The biofilm growths attached to the particles, which are expanded by the upward velocity of the liquid, increased by the high rate of recirculation applied. The expansion of the bed is maintained at a level required for each support particle to preserve its relative position to each of the other particles inside the bed. The expansion and fluidization of the medium reduces or eliminates blockage problems, besides increasing the biomass retention and its contact with the substrate, thereby allowing significant reductions in the hydraulic detention times in the reactors. In this figure, we can see a schematic representation of an expanded fluidized bed reactor. The influent flows through the system and the effluent is collected in the top of the reactor. For the system, there is a recirculation of part of the flow that guarantees an expansion or fluidization of the bed. The expansion of the bed is maintained at a level required for each support particle to preserve its relative position to each of the other particles inside the bed. The expansion of the bed is usually maintained between 10 and 20%. The operating principles of fluidized bed reactors are basically the same as those of the expanded bed reactors, except for the size of the particles of the support medium and the expansion rates. A high recirculation rate is required and, as a result, each independent particle does not maintain a fixed position inside the bed. The expansion of very thin particles guarantee a very large surface area for the growth of a uniform biofilm around each particle. The expansion degree usually varies between 30 and 100%. In this case, the upward velocity of the liquid should be sufficiently high to fluidize the bed until it reaches the point at which the upward drag force is equaled by the gravitational forces. Dear students, here we finish our class of attached growth in the high-rate systems. In the next meeting, we will explore the high-rate systems with dispersed growth. See you!